Welcome back to the next video, everybody. Today's video will be on how irreducibility of the residual mod 3 representation attached to an elliptic curve over Q implies the modularity for that representation. And I will give the first 3 of 4 steps today to keep the video shorter. Okay, so the strategy is as follows. We're going to take Langlands-Tunnell for granted, and we're going to show that rho bar E3 is irreducible implies rho bar E3 is modular. So the strategy is we're going to end up lifting rho bar E3 to a representation that we will call rho from GQ to GL2 of C. So it'll be a two-dimensional complex representation. This representation will satisfy the conditions of Langlands-Tunnell. And so by Langlands-Tunnell, we'll end up with a new form G of weight 1, whose Fourier coefficients equal to the trace of Frobenius at Q for almost all primes Q. So see the last video. We'll then end up multiplying G by a certain well-chosen Eisenstein series of weight 1, and its non-trivial Fourier coefficients will all be congruent to 0 mod 3. And so that product will end up being the required new form of weight 2, whose Fourier coefficients are congruent to the trace of Frobenius at Q mod some prime lying above 3, which is what we want, because that will give us something congruent to Q plus 1 minus the number of FQ points on E for almost all primes Q by one of the 2 crucial properties of rho bar EP that I listed last video. Okay, so that's the overall kind of global strategy. Okay, so what are the steps? There are 4 steps to this. Step 1, we're going to take rho bar E3, which goes from GQ to GL2 of F3, and we're going to extend it to a complex representation rho from GQ to GL2 of C. And how are we going to do that? We're going to compose with a certain injective group homomorphism, psi, from GL2 of F3 to GL2 of Z adjoin root -2. I've seen this described as happenstance, like we sort of get lucky that this happens here so that we can actually do this. Like randomly, this just embeds into GL2 of this Z adjoin root -2. Like that's nice, that's convenient, sure. And so what is this homomorphism? Well, I just have to tell you what it does on generators of GL2 F3. It'll take psi will take the matrix -1, 1, -1, 0 to -1, 1, -1, 0. And it will take 1, -1, 1, 1 to 1, -1, negative root -2, -1 plus root -2. And the reason that these generators were chosen is they're just kind of simple, easy to work with generators of GL2 of F3. Okay? And it's really easy to check that this map is an injective continuous group homomorphism. It's also not hard to check that the trace of psi of G is equivalent to the trace of G mod 1 plus root -2, and that the determinant of psi of G is equivalent to the determinant of G mod 3. Okay, so these are all exercises that I would recommend that you do. They're not challenging. Okay, so step 2, what do we have to do now? To apply Langlands-Tunnell, we have to make sure that we have a representation to which we can apply it. So we'll let rho be psi compose rho bar E3, which is of course a representation from GQ to GL2 of C. This is our candidate guy that's going to satisfy the conditions of Langlands-Tunnell. That is, we have to make sure that rho is odd, irreducible, and solvable in order to apply the theorem. So let's do that. So oddness, well, if C denotes complex conjugation, we definitely know that det rho bar E3 of C is -1 because we already know rho bar E3 is odd, right? But on the other hand, C squared is just 1, right? And so det of rho of C is definitely either plus or minus 1. But then remember, we have the determinant congruence relation up here that det of psi of G is equivalent to det of G mod 3. If you look at what that says, applied to our specific situation, what it says is that det of rho of C is equivalent to det of rho bar E3 of C mod 3. Okay, but I mean, the point is that det of rho of C can't be 1 because 1 isn't equivalent to -1 mod 3. And so det of rho of C must be -1 because that's the only other option, right? Perfect. So we have an odd representation. Why do we have a solvable representation? Well, it's a standard group theory fact that PGL2 of F3 is isomorphic to S4. You can see Rogers' small projective groups for a pretty easy proof of that. Well, that means the image of rho in PGL2 of C is just a subgroup of S4, right? Because psi is injective. Okay, well, that means the image is solvable. Done. Okay, how about irreducibility? Now, the argument I read for this, I didn't fully understand, so I've tried to fill in the details. I hope I've done so correctly. I've had a few people skim over it and tell me it's correct, but we'll see what you guys think. So here's the idea. You know that the determinant of rho bar E3 of C is -1. Because of that, rho bar E3 has distinct eigenvalues in F3, which are going to have to be plus or minus 1. Okay. Now that this implies, this is just a check, the only matrices in M2 of F3 bar commuting with the image of rho bar E3 are the scalar matrices lambda I. And so there's an operative converse to Schur's lemma that applies here to tell us that rho bar E3 is absolutely irreducible. Okay, but that's not what I want. What I actually want is that rho itself is irreducible. Okay, so I'll suppose rho isn't irreducible. By Moschke's theorem, any complex representation of a finite or a compact group, which is our situation, our representation is on GQ, which is compact, is completely reducible. Okay, so I'm going to apply that to my situation. I'm working in GL2 of C, so I'm working two-dimensionally here. So the only way this is possible is if rho is the sum of two characters along the diagonal, right? But that would make rho abelian, which means, if you haven't heard that before, that just means the image is abelian. So that's just a quick check that if rho is the sum of two characters, then it's abelian. There's nothing to it. Okay, but then by actual Schur's lemma, since rho bar E3 is absolutely irreducible, the only matrices commuting with its image in GL2 of F3 bar are the scalar matrices. Well, if you pull all this information back through the injection psi, what you have right now is that rho bar E3 has an abelian and an irreducible image in GL2 of F3 bar, which is of course impossible. Because again, abelian images here are exactly the sums of two characters, which are reducible. Okay, that's a contradiction, right? So rho is irreducible. All right. So step 3, what's step 3? Well, I can apply Langlands-Tunnell to rho now because I meet all the criteria. So Langlands-Tunnell gives me a new form G with Fourier coefficients B sub n in S1 of gamma 0 n1 epsilon 1 for some epsilon 1 and n1. And I know that BQ, the Q Fourier coefficient here, is trace of rho for being set Q for almost all primes Q, as usual. Okay, and then before going on to the last slide, I just want to make a remark here. You recall from chapter 3 of my notes, the coefficients of a new form of weight K, at least one, lie in the ring of integers OK of some number field K. And so this is to say that it makes sense to talk about congruence conditions on our coefficients B sub n in G modulo prime ideals frac P of an appropriately chosen OK. And that's going to matter in just a second here. We're going to have to be able to talk about that. And so last slide for the day. So recall, what is trace of rho of frob Q? It's trace of psi of rho bar E3 of frob Q by definition of rho. But that's equivalent to trace of rho bar E3 of frob at Q mod 1 plus root negative 2 by the trace congruence relation that I gave you above. And so if you take the data we just gathered from Langlands-Tunnell and properties from the last video, and then the remark I just gave you, you tie that all together, what you end up with is that BQ is equivalent to Q plus 1 minus the number of FQ points on E mod frac P for almost every prime Q, and for some prime frac P of Q bar lying over 1 plus root negative 2, the ideal. But 1 plus root, this lies over 3, right? So this prime frac P lies over 3. Okay, fine. Well, then that gives me that rho bar, that gives me that rho bar E3 by definition is modular, but the problem is it's weight 1, right? We want it to be modular of weight 2. And so that'll be step 4, and we'll look at how to do that next time. So thanks for watching, and I'll see you then.